For over 400 years, astronomers have been staring at our own galaxy completely blind. We thought we knew the Milky Way. We were wrong. Hidden behind cosmic dust clouds, millions of stars have been invisible to us. Entire spiral arms, secret star factories, the true shape of our cosmic home. But now, revolutionary infrared technology has ripped away the veil. We'll journey through hidden stellar nurseries where giants are born, discover the galaxy's violent past, written in starlight, and uncover how our cosmic address just got rewritten. If you're ready to see our galaxy like never before, hit that like button and subscribe. The revelation begins now. Imagine trying to map your house while standing inside a thick fog. That's exactly the problem astronomers have faced for centuries when studying our own galaxy. We live inside the Milky Way, embedded deep within its disk, surrounded by stars and cosmic debris that block our view. It's like being a single person standing in the middle of Times Square during a snowstorm, trying to draw a map of New York City. When Galileo first pointed his telescope at the night sky in 1609, he saw the Milky Way's cloudy band resolve into countless individual stars, but he had no idea he was looking at the edge-on view of a massive spiral galaxy. No idea that our sun was just one ordinary star among 400 billion others. No idea that we were spinning through space at 500,000 miles per hour, trapped in a cosmic whirlpool larger than anything humans had ever imagined. For the next 3 centuries, astronomers tried to piece together our galaxy's structure using visible light alone. They mapped where stars appeared brightest and where they seemed to fade away. They counted stellar densities in different directions. They measured how stars moved through space. But every observation was fundamentally limited by the same cruel fact. Visible light can't travel very far through the galaxy before something blocks it. Think of it like trying to see across a crowded stadium during a fog machine concert. The lights are there, but layers of haze keep you from seeing the back rows. In space, that haze is cosmic dust. Tiny particles of silicon, carbon, and iron scattered throughout the galaxy like microscopic sand. These dust grains are so small that 10,000 of them lined up wouldn't span the width of a human hair. Yet, they're everywhere, floating between the stars in vast clouds that stretch for hundreds of light years. The dust doesn't just dim starlight, it completely blocks it. A dust cloud only a few light years thick can hide an entire star cluster containing thousands of suns. Some of the most massive stars in our galaxy, giants that burn 1,000,000 times brighter than our sun, remain completely invisible to optical telescopes because they're hidden behind these cosmic curtains. By the 1950s, astronomers realized they had mapped less than 10% of the Milky Way. The other 90% remained hidden behind dust. They could see individual stars within a few thousand light years of Earth, but beyond that, their view was blocked. They were like archaeologists trying to study an ancient city while wearing blindfolds, feeling around in the dark for clues about what lay buried beneath. The galaxy's true spiral arms, its central black hole, its complete population of stars, the secret stellar nurseries where new suns are born, all of it remains shrouded in mystery. We knew we lived in a spiral galaxy because we could study distant galaxies that looked similar to what we thought ours might look like. But we were guessing about our own cosmic home. What astronomers needed was a way to see through the dust entirely. They needed a different kind of light that could pierce the cosmic fog and reveal what had been hidden for so long. But what kind of light could possibly penetrate clouds so thick they had fooled humanity for centuries? Cosmic dust isn't like the dust bunnies under your bed. These microscopic particles are the cremated remains of ancient stars scattered across space in clouds so vast they could swallow our entire solar system and still have room for 1,000 more. When massive stars die in supernova explosions, they blast their guts across hundreds of light years, seeding space with silicon, carbon, oxygen, and iron. Over millions of years, these particles clump together into the cosmic equivalent of smoke clouds, floating between the stars like ghosts of stellar death. Each dust grain is smaller than the particles in cigarette smoke. You could fit 50,000 of them across the period at the end of this sentence. But what they lack in size, they make up for in sheer quantity. Our galaxy contains enough cosmic dust to build 10 million planets the size of Earth. If you could gather all the dust in the Milky Way into one place, it would outweigh our sun by several times over. The problem isn't just how much dust there is, it's where the dust likes to hang out. Cosmic dust gravitates toward the galaxy's disk, the same flat plane where most stars live, including our sun. Think of a snow globe that's been shaken and then left to settle. All the artificial snow sinks to the bottom, creating a layer that blocks your view across the globe. That's exactly what happens in our galaxy, except the snow is cosmic dust and the globe is 400 billion stars spinning through space. From our position inside the galactic disk, we're surrounded by this dust. When we look toward the center of the galaxy, we're staring through thousands of light years of accumulated particles. When we look along the galaxy's spiral arms, the dust is so thick it's like trying to see through chocolate milk. Only when we look up or down out of the galactic plane can we see clearly into intergalactic space. That's why we can observe distant galaxies billions of light years away. But we can't see what's happening in our own galactic backyard. The dust affects different colors of light in different ways. Blue light gets scattered and absorbed much more easily than red light, which is why sunsets look red when viewed through Earth's dusty atmosphere. In space, this means blue stars become invisible long before red stars do. But even red light can only travel so far before the cumulative effect of countless dust grains blocks it completely. By the middle of the 20th century, astronomers had mapped the dust's distribution and realized the full scope of their problem. They could see roughly 5,000 light years in most directions before cosmic dust made further observation impossible. But the Milky Way stretches over 100,000 light years from edge to edge. They were seeing less than 5% of their own galaxy. The dust had created the ultimate cosmic conspiracy, hiding the galaxy's secrets in plain sight. Star clusters containing hundreds of thousands of suns remained completely invisible. Entire spiral arms disappeared behind dusty veils. The galaxy's most active star-forming regions, where cosmic creation happens on an industrial scale, were locked away behind impenetrable barriers. But astronomers were about to discover that dust, for all its power to block visible light, had one critical weakness. The cosmic dust that had fooled humanity for centuries had never encountered infrared light. Infrared radiation is invisible to human eyes, but it's everywhere around us. Your warm coffee mug emits infrared light. Your body radiates infrared energy. Even ice cubes glow brightly in infrared wavelengths. This thermal radiation carries a wavelength roughly 10 times longer than visible light, and that difference changes everything when it comes to cosmic dust. Think of trying to throw basketballs versus ping pong balls through a chain link fence. The ping pong balls get blocked and bounce off the wires, but the basketballs sail right through the gaps. Infrared light behaves like those basketballs. Its longer wavelength allows it to slip past dust particles that easily block visible light. Where visible light sees an impenetrable wall, infrared light sees an open highway. The breakthrough came in the 1960s when astronomers launched the first infrared telescopes above Earth's atmosphere. Our planet's atmosphere absorbs most infrared radiation, so ground-based infrared astronomy was nearly impossible. But from space, infrared detectors could peer through the galaxy's dusty veil for the first time in human history. What they discovered was revolutionary. Stars that were completely invisible to optical telescopes blazed like beacons in infrared light. Dust clouds that had blocked visible light for millions of years became transparent, revealing the stellar treasures hidden within. Entire star-forming regions shrouded since the galaxy's birth suddenly became accessible to human observation. The effect was so dramatic, it was like someone had switched on cosmic X-ray vision. Astronomers could finally see through the galaxy's walls. The central regions of the Milky Way, hidden behind 26,000 light-years of dust, became visible for the first time. The galaxy's spiral arms, invisible in optical light, emerged from their dusty cocoons. Star clusters containing hundreds of thousands of suns materialized out of what had appeared to be empty space. But infrared light revealed more than just hidden stars. The dust itself began to glow. When cosmic dust absorbs visible and ultraviolet light from nearby stars, it heats up and re-radiates that energy as infrared light. This meant astronomers could map the dust clouds themselves, seeing their intricate structure in exquisite detail. They could trace how gas and dust flow through the galaxy, how it clumps together to form new stars, and how stellar explosions blast it back into space. The revelation was like discovering that your house had secret rooms you never knew existed. The Milky Way wasn't the galaxy astronomers thought they had been studying for 4 centuries. It was larger, more complex, more dynamic, and filled with structures that had been completely invisible. The population of stars was far greater than anyone had imagined. The galaxy's spiral pattern was more intricate and beautiful than optical observations had suggested. By the turn of the 21st century, infrared astronomy had opened new windows into the cosmic deep, but the technology was still limited. Early infrared surveys could only map small patches of sky at relatively low resolution. What astronomers really needed was a systematic, comprehensive infrared survey of the entire galaxy. What they needed was a revolutionary telescope that could map our cosmic neighborhood with unprecedented detail and precision. High in Chile's Atacama Desert sits a telescope that can see what 4 centuries of astronomy could not. VISTA, the Visible and Infrared Survey Telescope for Astronomy, perches on a mountaintop 2.5 miles above sea level, where the air is so thin and dry that infrared light from space can reach Earth virtually unfiltered. This 4-meter mirror, wider than a compact car, represents the largest infrared survey telescope ever built. But size alone isn't what makes VISTA revolutionary. It's what the telescope can do with that massive mirror that changes everything. VISTA doesn't just take pretty pictures of individual cosmic objects. It systematically maps enormous swaths of sky with the precision of a cosmic cartographer. Think of the difference between taking a single photograph of your neighborhood versus flying a drone equipped with high-resolution cameras over your entire city, photographing every building, every street, every park, and then stitching millions of images together into one comprehensive map. That's what VISTA does for our galaxy. The telescope's secret weapon is its camera, a marvel of engineering containing 67 infrared detectors cooled to -300 degrees Fahrenheit. At these frigid temperatures, the detectors become sensitive enough to capture individual photons that have traveled thousands of light years through space, dodging dust clouds and navigating the galaxy's magnetic fields before arriving at Earth. Each detector is more sensitive than the most advanced night vision goggles, capable of seeing infrared sources millions of times fainter than what the human eye can detect. But VISTA's true genius lies in its systematic approach. Rather than randomly pointing at interesting objects, the telescope follows carefully planned survey strategies that map specific regions of the galaxy in multiple infrared wavelengths. It's like having superhuman vision that can switch between different types of X-ray vision, each revealing different aspects of the same cosmic landscape. Some wavelengths reveal hot young stars, others highlight cool old giants, and still others trace the warm glow of cosmic dust itself. The VISTA variables in the Via Lactea survey, known as VVV, has spent over a decade photographing the most dust-obscured regions of our galaxy. Night after night, VISTA returns to the same patches of sky, building up incredibly detailed infrared portraits of stellar neighborhoods that have never been clearly seen before. The telescope captures so much data that it fills computer hard drives faster than astronomers can analyze it. Each VISTA image contains roughly 67 million individual measurements of starlight. A single night of observing generates enough data to keep astronomers busy for months. The survey has now accumulated over 500 terabytes of infrared imagery, creating the most detailed infrared atlas of the Milky Way ever assembled. That's enough data to fill more than 100,000 DVDs stacked 2 miles high. This systematic approach has allowed astronomers to create the first truly comprehensive 3-dimensional map of our galaxy's hidden architecture. For the first time in human history, we can see the Milky Way's complete structure, from its innermost regions to its outermost spiral arms. And what VISTA found hiding in those cosmic shadows would rewrite our understanding of how many stars our galaxy actually contains. Within weeks of beginning its survey, VISTA discovered 96 star clusters that had been hiding in plain sight. These weren't small groups of a few dozen stars scattered randomly through space. These were massive stellar cities, each containing thousands or tens of thousands of stars bound together by gravity, some older than complex life on Earth. They had been sitting there all along, invisible to every optical telescope ever built, waiting patiently for infrared eyes to finally see them. Star clusters are like stellar families, born together from the same cosmic cloud and aging together over millions or billions of years. When astronomers find a cluster, they're discovering a complete stellar ecosystem with its own history, its own population of different star types, and its own story of cosmic evolution. Finding one new cluster is exciting. Finding nearly 100 in a few months of observation was unprecedented. Think of like discovering that your city has dozens of hidden neighborhoods that were invisible until someone invented special glasses that could see through fog. Suddenly, entire communities that you never knew existed are revealed, each with its own character, its own population, its own unique features. That's exactly what happened when Vista turned its infrared vision toward the dustiest regions of our galaxy. The clusters Vista found weren't randomly distributed. Many were concentrated near the galaxy's center, hidden behind the thickest dust clouds. Others were embedded in the galaxy's spiral arms, camouflaged within star-forming regions where cosmic gas and dust create nearly impenetrable barriers to visible light. Some clusters were so heavily obscured that they absorbed over 99% of their visible light before it could reach Earth. One of the most dramatic discoveries was a cluster hiding behind the constellation Sagittarius, buried so deep in cosmic dust that optical telescopes saw nothing but darkness. Vista revealed it contains over 10,000 stars, making it one of the most massive clusters in our galactic neighborhood. This stellar metropolis had been completely invisible for the entire history of human astronomy, despite being relatively close to Earth at only 15,000 light-years away. Another hidden cluster turned out to be incredibly ancient, containing stars over 10 billion years old. These stellar fossils formed when our galaxy was young and chaotic, preserving clues about the Milky Way's violent early history. Finding such old clusters in heavily dust-obscured regions suggests that our galaxy's structure has been more dynamic and complex than astronomers previously realized. Each newly discovered cluster represents a piece of the galactic puzzle that was missing from every previous map of our cosmic neighborhood. The clusters contain different populations of stars, different ages, and different chemical compositions, all telling unique stories about how different regions of the galaxy have evolved over cosmic time. But the hidden clusters were just the beginning. As Vista continued its systematic survey, pushing deeper into previously unexplored regions of infrared sky, it began revealing something even more remarkable. Behind the cosmic dust scattered throughout the galaxy's most obscured regions, millions of individual stars were about to emerge from their shadowy hiding places. Vista's infrared eyes revealed that our galaxy contains 3 billion more stars than astronomers had ever seen before. 3 billion. That's like discovering that Earth's population is actually twice what we thought it was, with entire continents of people living in places we couldn't see. These weren't dim, distant stars at the edge of the galaxy. Many were massive, bright giants hiding behind dust clouds, some burning hundreds of times more intensely than our sun. They had been there all along, pumping out enormous amounts of energy, influencing their cosmic neighborhoods, and playing crucial roles in the galaxy's evolution. We just couldn't see them. The discovery happened gradually as Vista systematically mapped one region of sky after another. Each new patch of infrared imagery revealed stars where optical telescopes saw only darkness. At first, astronomers found thousands of new stars, then tens of thousands, then hundreds of thousands. As the survey expanded and pushed deeper into the galaxy's most dust-obscured regions, the count climbed into the millions. Think of it like using thermal imaging to explore a dark forest. With visible light, you might see scattered trees and clearings. But thermal vision reveals the warm bodies of countless animals hiding in the underbrush, behind tree trunks, and in the shadows. Suddenly, what appeared to be a quiet woodland becomes a thriving ecosystem, teeming with life you never knew existed. Many of these hidden stars turned out to be red giants, enormous stellar furnaces in the final stages of their lives. These swollen stars have exhausted the hydrogen fuel in their cores and expanded to incredible sizes. Some are so large they could swallow the orbit of Mars. Despite their massive size and intense energy output, cosmic dust had rendered them completely invisible to optical observation. Others were young, hot stars recently born from collapsing gas clouds. These stellar newborns burn with such intensity that they ionize the surrounding space, creating bubbles of superhot plasma that stretch for dozens of light years. Their ultraviolet radiation sculpts the cosmic landscape around them, clearing out gas and dust and triggering the formation of new generations of stars. Yet dust clouds had hidden these cosmic powerhouses from human observation for their entire existence. The revelation extended far beyond simple star counting. Each newly visible star provided a data point for understanding the galaxy's structure, composition, and history. Astronomers could finally measure how stars are distributed throughout the galaxy's disk. They could trace the spiral arm's true shape and extent. They could map stellar populations that had been completely unknown. Some of the most dramatic discoveries came from the galaxy's central regions, where dust extinction is so severe that optical telescopes can barely penetrate a few hundred light years toward the galactic center. VISTA revealed vast populations of stars surrounding the central black hole, creating a three-dimensional picture of our galaxy's heart for the first time. But individual stars weren't the only cosmic structures emerging from their dusty hiding places. Deep within the galaxy's most obscured regions, VISTA was about to unveil entire stellar factories, where new suns are manufactured on an industrial scale. Behind cosmic dust clouds, VISTA discovered star factories operating at full capacity for millions of years. These stellar nurseries are vast regions where gravity slowly crushes enormous clouds of gas and dust until they collapse into newborn stars. The process takes millions of years and happens inside cocoons of cosmic material so thick that no visible light can escape. For centuries, astronomers knew these star-forming regions existed because they could detect their radio emissions and measure their gravitational effects, but they had never actually seen the stellar birth process happening. VISTA changed that by revealing the intricate details of cosmic creation in infrared light. Suddenly, astronomers could peer inside stellar wombs and watch as gravity sculpted raw cosmic material into glowing stellar embryos. They could see protostars, the earliest phase of stellar development, as warm infrared sources slowly accumulating mass from their surrounding disks. They could trace how stellar winds and radiation from newly formed stars carved out cavities in their birth clouds, creating space for the next generation of stellar formation. Think of it like being able to see inside eggs as baby birds develop, watching each stage of growth from the first cell divisions to the moment they hatch. VISTA revealed star formation as a dynamic, ongoing process, rather than a mysterious event hidden behind impenetrable barriers. One of the most spectacular discoveries was a massive star-forming complex hidden behind the constellation Cygnus. Optical telescopes saw this region as a dark patch of apparently empty sky, a cosmic void where nothing seemed to exist. VISTA revealed it contains over 2,000 newly forming stars, making it one of the most active stellar nurseries in our galactic neighborhood. The region is so productive that it's creating the equivalent mass of our sun in new stars every few thousand years. Another hidden nursery was found embedded within what appeared to be an ordinary dust cloud near the galactic center. VISTA's infrared vision revealed dozens of massive protostars in various stages of development. Some were already igniting their nuclear furnaces, while others were still accumulating material from their surrounding disks. The discovery showed that star formation continues even in the galaxy's most crowded and chaotic regions. These stellar nurseries operate like cosmic assembly lines, continuously converting raw gas and dust into finished stars. The process begins when shock waves from nearby stellar explosions or galactic collisions compress vast molecular clouds. Gravity takes over, creating dense knots that slowly collapse over millions of years. As material falls inward, it heats up and begins to glow in infrared light, creating the warm signatures that VISTA can detect. The infant stars don't form in isolation. They're born in groups, creating entire stellar families that will eventually disperse throughout the galaxy. Some nurseries produce dozens of stars. Others manufacture hundreds or thousands in massive stellar boom periods that can last for tens of millions of years. But VISTA wasn't working alone in revolutionizing our understanding of galactic architecture. Another space mission was simultaneously conducting its own precision measurements that would complement VISTA's discoveries in unexpected ways. While VISTA was revealing hidden stars, the Gaia spacecraft was measuring their positions with accuracy that defies human comprehension. Launched in 2013 to orbit the Sun at a distance of 1 million miles from Earth, Gaia carries the most precise star-measuring instrument ever built. Its mission is deceptively simple: measure the exact position, distance, and motion of every star it can see. But the precision required is so extreme, it's like measuring the width of a human hair from 3,000 meters away. Gaia works by detecting tiny changes in stellar positions as Earth orbits the Sun. When we view a relatively nearby star from opposite sides of Earth's orbit, the star appears to shift slightly against the background of more distant stars. This shift, called parallax, is incredibly small. For most stars, the angular change is measured in milliarc seconds, units so tiny that 1 milliarc second is equivalent to seeing a quarter from 2,000 meters away. Think of trying to measure how far away a streetlight is by closing one eye, then the other, and noting how the streetlight seems to jump against distant mountains. Now imagine doing that measurement so precisely you could detect movements smaller than the width of bacteria. That's the level of accuracy Gaia achieves for millions of stars simultaneously. The spacecraft spins slowly in space, sweeping its twin telescopes across the entire sky every 6 hours as it rotates. Gaia's billion-pixel camera captures the precise positions of any stars that drift across its field of view. By repeating these measurements over several years, the spacecraft can detect the incredibly subtle parallax shifts that reveal stellar distances with unprecedented accuracy. But Gaia does more than just measure where stars are located. It also tracks how they're moving through space. By comparing stellar positions taken months or years apart, Gaia can detect the proper motion of stars, their movement across the sky, perpendicular to our line of sight. For many stars, these motions are so slow that it would take centuries for human eyes to notice any change. But Gaia's precision is so extreme it can measure stellar movements equivalent to watching grass grow from the moon. The combination of precise distances and motions allows astronomers to reconstruct the three-dimensional architecture of our galactic neighborhood with extraordinary detail. Instead of seeing stars as points of light projected onto a flat sky, Gaia reveals them as objects moving through three-dimensional space, each following its own orbital path around the galactic center. When Gaia's first major data release arrived in 2016, it contained precise measurements for over 1 billion stars. The second data release in 2018 added stellar velocities, chemical compositions, and surface temperatures. Each release transformed our understanding of galactic structure, revealing patterns and connections that had been completely invisible to previous generations of astronomers. But the real magic happened when astronomers began combining Gaia's precision position measurements with VISTA's infrared discoveries, creating something that had never existed before in human history. Combining VISTA's infrared discoveries with Gaia's precision measurements created the first true three-dimensional map of our galactic neighborhood. For thousands of years, humans have looked up at the night sky and seen what appears to be a flat dome studded with points of light. The stars seem to exist on a two-dimensional surface, like jewels scattered across black velvet. But that's an illusion created by the limitations of human perception. In reality, stars exist in three-dimensional space, some relatively nearby and others fantastically distant, all moving in complex orbits around the galactic center. Creating a three-dimensional map from what appears to be a flat sky requires solving one of astronomy's most fundamental challenges: determining distance. When you look at two stars that appear next to each other in the sky, you have no way of knowing whether they're actually close together in space or just happen to line up from your perspective. One star might be 50 light years away, while its apparent neighbor could be 50,000 light years distant. Think of looking at a city skyline from a mountain peak. Two buildings might appear to be right next to each other, but one could be a small structure in the foreground, while the other is a massive skyscraper miles away in the background. Without depth perception, you can't distinguish between them. That's exactly the problem astronomers face when studying stellar positions. Gaia solved this problem by measuring parallax with unprecedented precision, allowing astronomers to calculate exact distances to millions of stars. But parallax only works for relatively nearby stars. Beyond a few thousand light years, even Gaia's incredible precision isn't enough to detect the tiny angular shifts needed for distance measurement. That's where VISTA's discoveries became crucial. The infrared telescope revealed millions of stars that were completely invisible to Gaia because cosmic dust blocked their visible light. But many of these hidden stars belong to stellar populations with known properties, red giants of specific ages, or young hot stars with predictable characteristics. By measuring the infrared brightness of these stars and comparing it to their expected intrinsic luminosity, astronomers can calculate their distances using a technique called photometric parallax. When combined with Gaia's precision measurements of nearby stars, this creates a three-dimensional stellar census that extends throughout the galaxy. Astronomers can now plot not just where stars appear to be in the sky, but where they actually exist in three-dimensional space. They can trace stellar orbits, map stellar populations, and reconstruct the galaxy's structure in exquisite detail. The resulting maps look like nothing humans have ever seen before. Instead of flat star charts, astronomers now work with interactive three-dimensional models where they can rotate the galaxy, zoom into specific regions, and follow individual stars as they move through space over millions of years. They can slice through the galactic disk at different angles, revealing hidden structures and unexpected patterns. But when astronomers began analyzing these three-dimensional maps in detail, they discovered something that would fundamentally challenge everything they thought they knew about our galaxy's shape. The Milky Way isn't the neat, flat disk that astronomy textbooks have depicted for decades. When astronomers analyzed the three-dimensional positions of millions of stars revealed by VISTA and Gaia, they discovered that our galaxy is twisted into a complex, warped shape like a vinyl record left on a hot dashboard. The galactic disk bends and curves in ways that completely contradict the simple spiral galaxy models that have dominated astronomy education for generations. The warping becomes more pronounced toward the galaxy's outer edges, where the disk curves both upward and downward from the galactic plane by thousands of light years. If you could view the Milky Way edge-on from outside our galaxy, it would look like a cosmic saddle or a gently twisted ribbon stretching across space. The effect is so subtle that it could only be detected by mapping the precise three-dimensional positions of individual stars across vast distances. Think of trying to detect whether a massive dinner plate is perfectly flat by examining the positions of individual salt grains scattered across its surface. If the plate has even the slightest warp or bend, the salt grains on one side will be slightly higher or those on the other side. But you'd need to measure the position of each grain with incredible precision to detect such subtle deformations. That's exactly what Gaia and VISTA accomplished for our galaxy. The discovery explains several astronomical mysteries that had puzzled scientists for decades. Radio astronomers had detected hydrogen gas clouds that seemed to exist above and below the galactic plane in patterns that didn't match theoretical models. Now we know these gas clouds are following the galaxy's true warped structure, distributed along curves and bends that were invisible until we could map stellar positions in 3 dimensions. The warping isn't random. It follows specific patterns that suggest our galaxy has been gravitationally influenced by its 2 largest satellite galaxies, the Large and Small Magellanic Clouds. These companion galaxies have been orbiting the Milky Way for billions of years, and their gravitational pull has gradually twisted our galaxy's outer regions like a cosmic slow-motion dance. But the warping is dynamic, not static. Computer simulations based on the new 3-dimensional data show that the galaxy's shape changes over time as it rotates. Different regions of the disk curve upward and downward in a wave-like pattern that travels around the galaxy every few hundred million years. We're not living in a rigid, unchanging structure, but in a flexible, evolving cosmic environment that breathes and flexes as it spins through space. The discovery has forced astronomers to completely revise their understanding of galactic dynamics. The Milky Way isn't an isolated system quietly spinning in empty space. It's part of a complex gravitational ecosystem where nearby galaxies, dark matter halos, and cosmic gas flows all contribute to shaping its structure over cosmic time. But the galaxy's warped shape was just the beginning of the structural surprises hiding in the three-dimensional data. When astronomers looked more closely at the disk's spiral pattern, they found evidence of galactic architecture that was far more complex and beautiful than anyone had imagined. Our galaxy has been hiding entire spiral arms that were completely invisible to optical telescopes. For over a century, astronomers thought they had mapped the Milky Way's spiral structure based on observations of bright young stars and glowing gas clouds. They identified 4 major spiral arms wrapping around the galactic center, creating the classic pinwheel pattern familiar from astronomy textbooks. But those observations were fundamentally limited by cosmic dust, which blocked the view of spiral arms on the far side of the galaxy and obscured structures in the galactic plane. When VISTA's infrared data was combined with Gaia's three-dimensional measurements, the galaxy's true spiral pattern emerged for the first time. What astronomers discovered was a spiral structure far more intricate and extensive than anyone had imagined. Hidden spiral arms emerged from behind dust clouds, some extending much farther from the galactic center than previously known. Others appeared between the major arms, creating a complex network of stellar streams and bridges that connect different regions of the galaxy. Think of trying to map the layout of a vast city by standing on one street corner and looking only at the buildings you can see directly. You might identify a few major avenues and assume they represent the city's primary structure. But when you finally get access to aerial photography that can see through fog and haze, you discover an intricate network of smaller streets, alleys, and pathways connecting neighborhoods in ways you never suspected. One of the most dramatic discoveries was a previously unknown spiral arm extending from the far side of the galactic center. Hidden behind 26,000 light-years of dust and gas, this arm contains millions of stars and stretches for tens of thousands of light-years. Yet, it had been completely invisible to every previous astronomical survey. Its discovery suggests that the galaxy's spiral pattern is more symmetrical than optical observations had indicated. Another surprise was the discovery of what astronomers call feather structures, smaller spiral segments that branch off from the major arms like cosmic tributaries. These structures contain their own populations of stars and star-forming regions, creating a hierarchical spiral pattern that resembles the branching structure of river systems or blood vessels. The galaxy's spiral arms aren't simple isolated structures, but part of an interconnected network that channels gas, dust, and stars throughout the galactic disk. The new maps also revealed that spiral arms aren't permanent features carved in stone. They're dynamic structures that form, evolve, and dissipate over hundreds of millions of years as density waves propagate through the galactic disk. Stars move in and out of spiral arms as they orbit the galactic center, spending millions of years within spiral structures before continuing their journey through inter-arm regions. Perhaps most surprisingly, the infrared observations showed that some spiral arms contain populations of older stars that had never been detected before. These stellar fossils preserve evidence of the galaxy's spiral structure from billions of years ago, allowing astronomers to reconstruct how the Milky Way's spiral pattern has evolved over cosmic time. But spiral arms weren't the only galactic structures hiding behind cosmic dust. The three-dimensional maps revealed evidence of ancient cosmic violence written in the very architecture of our galaxy. Written in starlight, Gaia discovered the forensic evidence of cosmic crashes that nearly destroyed our galaxy. When astronomers analyzed the three-dimensional motions of millions of stars, they found something unexpected. Large groups of stars were moving through the galaxy in coordinated patterns that couldn't be explained by normal galactic rotation. These stellar streams were moving too fast in the wrong directions, with chemical compositions that didn't match their galactic neighborhoods. They were like cosmic refugees carrying the signatures of ancient catastrophes. The evidence pointed to a shocking conclusion. Our galaxy has been involved in multiple collisions with smaller galaxies over the past 10 billion years. Each collision left distinctive fingerprints in the stellar population, creating groups of stars with shared origins, similar ages, and unusual orbital patterns. These stellar archaeologists preserve the memory of cosmic violence that happened billions of years before Earth even existed. Think of examining a crime scene where the evidence has been scattered by wind and weather for decades. A skilled detective can still piece together what happened by analyzing the patterns of debris, the trajectory of scattered objects, and the chemical signatures left behind. That's exactly what astronomers are doing with stellar data, reconstructing galactic collisions from the orbital patterns and chemical compositions of stars that witnessed these cosmic catastrophes. The most dramatic discovery was evidence of a massive collision that happened 8 to 10 billion years ago, when a galaxy roughly 1/4 the size of the Milky Way smashed into our galactic disk. Astronomers named this destroyed galaxy Gaia Enceladus, after the mythological giant buried beneath Mount Etna. The collision was so violent it nearly tore apart the early Milky Way, scattering stars across vast distances and fundamentally reshaping our galaxy's structure. The collision left distinctive signatures throughout the galaxy. Stars from the destroyed galaxy have different chemical compositions than native Milky Way stars, containing higher ratios of certain elements that reveal their foreign origins. Their orbital patterns are also distinctive, following highly elliptical paths that carry them far above and below the galactic disk, unlike the circular orbits of stars born within the Milky Way. But Gaia Enceladus wasn't the only cosmic collision in our galaxy's violent past. The data revealed evidence of at least 6 smaller collisions, each involving galaxies containing millions or billions of stars. Some of these mergers happened recently in cosmic terms, within the past few billion years. Others occurred so long ago that their stellar debris has been scattered throughout the galaxy by 10 billion years of orbital motion. These discoveries completely changed our understanding of how galaxies grow and evolve. Rather than forming in isolation and slowly accumulating mass over time, galaxies like the Milky Way grow primarily through cannibalism, devouring smaller neighbors and incorporating their stellar populations. Our galaxy is not a pristine original structure, but a composite built from the remains of dozens of smaller galaxies consumed over cosmic time. The collision evidence also explains some of the galaxy's most puzzling features, including unusual stellar populations that had never fit standard models of galactic evolution. But the most dramatic remnants of galactic cannibalism were yet to be discovered. Surrounding our galaxy like cosmic spaghetti, Gaia discovered rivers of stars torn from galaxies that the Milky Way consumed alive. These stellar streams stretch for hundreds of thousands of light years, wrapping around our galaxy in long, thin ribbons of stars that share common origins, ages, and chemical compositions. They're the smoking guns of galactic cannibalism, preserving the shapes of destroyed galaxies long after their original structures have been ripped apart by the Milky Way's gravitational tides. When a smaller galaxy ventures too close to the Milky Way, our galaxy's massive gravitational field begins stretching it like cosmic taffy. The process, called tidal disruption, pulls stars away from the smaller galaxy's center, creating long streams of stellar debris that follow the orbit of their destroyed parent. It's like watching a flock of birds being scattered by hurricane winds, except the process takes hundreds of millions of years and involves billions of stars. Think of dropping a sugar cube into a flowing river. The water doesn't instantly dissolve the cube, but gradually pulls away tiny particles, creating a trail downstream that marks the cube's path through the water. Stellar streams work the same way, marking the orbital paths of destroyed galaxies as they spiral into the Milky Way's gravitational embrace. The most spectacular example is the Sagittarius stream, a ribbon of stars that wraps around our galaxy multiple times like the seam on a baseball. This stream contains the remains of the Sagittarius dwarf galaxy, which the Milky Way has been slowly devouring for over 1 billion years. Each time the dwarf galaxy completes an orbit around the Milky Way, our galaxy's gravity strips away more of its stars, adding them to the growing stream that now encircles our entire galactic neighborhood. Gaia's precision measurements revealed over 60 distinct stellar streams surrounding the Milky Way, each representing the death throes of a smaller galaxy. Some streams are relatively fresh, containing stars that were torn away within the past few billion years. Others are ancient, their stars scattered so widely that only sophisticated statistical analysis can identify their common origins. Each stream tells a unique story of cosmic destruction. The stars within a stream share similar chemical compositions, revealing what their parent galaxy was like before its destruction. They also share similar ages, allowing astronomers to determine when the galactic collision occurred. By mapping the three-dimensional positions and motions of stream stars, astronomers can even reconstruct the orbital history of destroyed galaxies, tracing their paths as they spiraled toward their doom. But stellar streams aren't just archaeological curiosities. They're actively reshaping our galaxy today. As stream stars orbit through the Milky Way, they gravitationally influence our galaxy's structure, contributing to the warping and heating of the galactic disk. Some streams pass directly through regions where the Milky Way is actively forming new stars, their gravitational wake triggering episodes of accelerated star formation. The discovery of stellar streams revealed that our galaxy is surrounded by the ghosts of its victims, cosmic crime scenes preserved in starlight for billions of years. But this galactic violence isn't random destruction. It's how galaxies like ours have grown and evolved throughout cosmic history. At the heart of our galaxy lurks a monster with the gravitational power to control stars from thousands of light years away. Sagittarius A*, the supermassive black hole anchoring our galaxy's center, weighs as much as 4 million suns crushed into a region smaller than our solar system. For decades, this cosmic beast remained hidden behind impenetrable walls of dust and gas, its presence detected only through radio emissions and the orbital motions of nearby stars. But Vista's infrared eyes finally revealed the black hole's true sphere of influence, exposing a region where gravity becomes so extreme it dominates the behavior of everything within 10,000 light years. Think of a massive whirlpool in the ocean that can pull floating objects toward its center from miles away. Ships caught in the outer edges might not even realize they're being drawn inward until it's too late to escape. That's exactly what happens to stars within the galaxy's central region, except the whirlpool is made of warped space-time, and the process takes millions of years to complete. Vista's infrared observations revealed thousands of stars orbiting the central black hole in highly elongated paths that carry them incredibly close to the point of no return. Some of these stars approach within a few billion miles of the black hole's event horizon, reaching speeds of over 12,000 miles per second at their closest approach. At these velocities, the stars experience time dilation effects that would make minutes pass like hours compared to clocks farther from the black hole. But the black hole's influence extends far beyond these death-defying stellar orbits. The three-dimensional maps revealed that the entire central region of our galaxy is organized around the black hole's gravitational field. Star formation patterns, gas flows, and even the distribution of cosmic dust all show the fingerprints of the black hole's immense gravitational pull. The black hole doesn't just passively sit at the galaxy's center. It actively feeds on material that ventures too close, creating an accretion disk of superheated gas that glows brightly in infrared light. When the black hole's appetite increases, it can outshine billions of stars, pumping enormous amounts of energy into the surrounding space. These feeding episodes blast jets of high-energy particles thousands of light years from the galactic center, sculpting vast bubbles of hot gas that extend above and below the galactic disk. The infrared observations also revealed something unexpected. The black hole's gravitational influence has been sculpting stellar populations for billions of years. Ancient stars near the galactic center show chemical signatures that can only be explained by repeated close encounters with the black hole's intense gravitational field. Some have been gravitationally slingshot to incredible velocities, while others have had their outer layers stripped away by tidal forces. But the central black hole is just one component of an even more mysterious architectural framework that shapes our galaxy's structure on the largest scales. Hidden throughout our galactic neighborhood lies an invisible scaffolding made of the universe's most elusive substance. Our galaxy is embedded within a massive halo of invisible matter that outweighs all the stars by 10 to 1. Dark matter doesn't emit, absorb, or reflect light of any wavelength. It interacts with normal matter only through gravity, making it completely invisible to every telescope ever built. Yet, this mysterious substance provides the gravitational scaffolding that holds our galaxy together and determines its overall shape and structure. Without dark matter, the Milky Way would have torn itself apart billions of years ago. Think of dark matter as the invisible skeleton inside a human body. You can't see the bones directly, but their structure determines the body's shape, supports its weight, and enables its movement. Similarly, dark matter creates an invisible framework that supports the galaxy's visible components and guides their evolution over cosmic time. The evidence for dark matter comes from the motion of stars and gas throughout the galaxy. When astronomers measure how fast stars orbit the galactic center at different distances, they find something impossible. Stars in the galaxy's outer regions are moving too fast. According to the laws of physics, these distant stars should be moving much more slowly, like planets in our solar system where more distant worlds orbit more slowly than those closer to the sun. But that's not what happens in galaxies. Stars throughout the Milky Way's disk all orbit at roughly the same speed, about 5,000 miles per hour, regardless of their distance from the galactic center. This can only be explained if the galaxy contains much more mass than we can see. Invisible mass that extends far beyond the visible stellar disk. Gaia's precision measurements of stellar motions have allowed astronomers to map this invisible dark matter halo in unprecedented detail. The data reveals that our galaxy sits at the center of a roughly spherical dark matter distribution that extends at least 3,000 light years from the galactic center, 3 times larger than the visible galaxy itself. This dark matter halo contains over 1 trillion solar masses of invisible material, creating the gravitational environment that allows spiral galaxies like ours to exist. But dark matter isn't uniformly distributed. Computer simulations based on Gaia's data suggest that the dark matter halo contains substructure clumps, streams, and smaller halos left over from ancient collisions with dark matter-rich dwarf galaxies. Some of these dark matter substructures might be massive enough to gravitationally influence the motions of nearby stars, creating subtle signatures that could be detected in future astronomical surveys. The dark matter halo also plays a crucial role in galactic evolution. It acts like a cosmic reservoir, storing vast amounts of gas that slowly falls inward to fuel ongoing star formation. The halo's gravitational field helps channel cosmic gas flows and protects the galaxy from disruptive encounters with neighboring galaxies. Perhaps most remarkably, the dark matter halo provides the stable gravitational environment that has allowed complex structures like spiral arms and stellar populations to evolve over billions of years. Without this invisible foundation, our galaxy would be a chaotic, ever-changing environment unsuitable for the long-term stellar evolution that eventually led to planets like Earth. But the galaxy's invisible architecture influences more than just its overall structure and actively guides the movement of individual stars across vast cosmic distances. Stars don't stay put. They're constantly migrating across the galaxy like cosmic nomads on journeys that span billions of years. Gaia's precision measurements revealed that stellar migration is one of the most important processes shaping galactic evolution, yet it had been completely invisible to previous generations of astronomers. Stars born near the galactic center can eventually end up in the outer suburbs, while stars that formed in the galaxy's peaceful outskirts sometimes spiral inward toward the chaotic central regions. This cosmic shuffling happens so slowly that human civilization could rise and fall 1,000,000 times during a single stellar migration. Think of rush hour traffic in a major city, except instead of cars changing lanes, entire stars are switching galactic neighborhoods over the course of hundreds of millions of years. Some stars get caught in gravitational traffic jams that slow their orbital motion, causing them to spiral inward toward the galactic center. Others receive gravitational kicks that accelerate them outward, carrying them to more distant galactic suburbs. The migration process is driven by the galaxy's spiral arms, which act like slow-moving gravitational waves that propagate through the galactic disk. When a star encounters a spiral arm, the gravitational influence of the arm's concentrated mass can slightly change the star's orbital energy. Over many encounters with different spiral arms, these tiny changes accumulate into major shifts in orbital radius. VISTA's infrared observations revealed the dramatic consequences of this stellar migration. Old, metal-rich stars that could only have formed near the galactic center where heavy elements are most abundant now exist throughout the galaxy's outer regions. Meanwhile, some areas near the galactic center contain surprisingly young stellar populations that must have migrated inward from their birth sites in the galaxy's outer disk. The discovery of stellar migration solved several long-standing astronomical puzzles. Astronomers had wondered why stellar chemical compositions vary so smoothly across the galactic disk, despite the fact that different regions have very different star formation histories. Migration provides the answer. Stars constantly mix throughout the galaxy, carrying their chemical signatures to new neighborhoods and homogenizing the overall stellar population. Our own sun is a migrant star. Based on its chemical composition and age, astronomers now believe the sun formed roughly 26,000 light-years from the galactic center, about 4,000 light-years closer than its current position. Over the past 4.5 billion years, gravitational interactions with spiral arms have gradually pushed our solar system outward, carrying Earth to its present location in what astronomers call the galactic habitable zone. This migration might have been crucial for the development of life on Earth. The galaxy's inner regions are more dangerous environments with higher rates of stellar explosions, intense radiation, and gravitational disruptions that could sterilize planetary surfaces. By migrating outward, our solar system may have escaped these hazards and found refuge in the galaxy's more stable outer regions. But stellar migration is just one way the galaxy preserves information about its past. Hidden within the chemical compositions and ages of migrant stars lies a detailed record of galactic history spanning billions of years. Every star in our galaxy is a time capsule carrying the chemical signature of when and where it was born. When astronomers analyzed the detailed chemical compositions of millions of stars revealed by VISTA and Gaia, they discovered that our galaxy preserves a complete fossil record of its own evolution stretching back over 13 billion years. Each star's atmospheric chemistry reflects the cosmic environment that existed when it formed, creating an archaeological archive written in starlight that spans nearly the entire age of the universe. Think of tree rings that record environmental conditions year by year, preserving information about rainfall, temperature, and atmospheric composition going back centuries. Stars work similarly, except instead of recording annual changes, they preserve the chemical composition of their birth clouds for billions of years. By analyzing the elemental abundances in stellar atmospheres, astronomers can reconstruct what the galaxy was like when those stars first ignited their nuclear furnaces. The oldest stars in our galaxy contain almost pure hydrogen and helium, the only elements that existed in the early universe. These stellar fossils formed when the galaxy was young and chaotic, before generations of massive stars had manufactured and dispersed the heavier elements that make planets and life possible. Finding these ancient stars is like discovering primitive organisms preserved in rocks from Earth's earliest geological periods. Younger stellar populations show progressively higher concentrations of heavier elements like carbon, oxygen, silicon, and iron. These metals were manufactured inside massive stars and scattered throughout the galaxy when those stars exploded as supernovae. Each stellar generation enriched the galactic environment with heavier elements, creating the chemical evolution that eventually made rocky planets and biological complexity possible. But the chemical fossil record reveals more than just gradual enrichment over time. Sharp changes in elemental abundances mark specific episodes in galactic history, when major events disrupted the normal process of stellar evolution. The collision with Gaia Enceladus 8 billion years ago, for example, left distinctive chemical signatures throughout the galaxy, as the destroyed galaxy's stars mixed with native Milky Way populations. Vista's infrared observations were crucial for this galactic archaeology because dust extinction had hidden many of the galaxy's oldest stellar populations. Cool, ancient red giant stars that formed during the galaxy's earliest epochs were often completely invisible to optical telescopes despite containing the most primitive chemical compositions. Infrared light revealed these stellar fossils for the first time, allowing astronomers to study the galaxy's chemical evolution in unprecedented detail. The chemical fossil record also reveals how different regions of the galaxy evolved at different rates. The galactic center experienced rapid star formation and chemical enrichment during the first few billion years, while the outer regions evolved more slowly and preserved more primitive stellar populations. Some globular clusters contain stars with chemical compositions so ancient they provide direct information about the conditions that existed when our galaxy first assembled from smaller building blocks. But hidden among these well-understood stellar populations, Vista discovered something completely unexpected: groups of stars that didn't fit any existing models of galactic evolution. Vista discovered entire communities of stars living in cosmic neighborhoods where they had no right to exist. These stellar misfits have chemical compositions, ages, and orbital patterns that contradict every model of how galaxies form and evolve. Young, metal-rich stars appeared in regions that should only contain ancient primitive populations. Ancient stars with bizarre chemical signatures showed up in areas where only recently formed stars should exist. It was like finding penguins in the Sahara Desert or palm trees in Antarctica, populations that had somehow ended up in completely wrong environments. Think of conducting a census in your city and discovering that some neighborhoods contain nothing but teenagers from the 1800s, while others are populated entirely by newborns who somehow possess advanced college degrees. That's the level of astronomical confusion these stellar populations created when astronomers first began analyzing their properties in detail. One of the most puzzling discoveries was a population of ancient stars hiding within the galaxy's thin disk, the region where our sun and most familiar stars reside. These stellar fossils are over 10 billion years old, yet they orbit the galaxy in the same flat plane as much younger stars. According to standard models of galactic evolution, such old stars should have been scattered into a thick, puffed-up distribution by billions of years of gravitational interactions. Finding them still confined to the thin disk was like discovering that some residents of an ancient city had somehow avoided aging while everyone around them grew old. Another surprise was the discovery of young star clusters in regions where star formation should have stopped billions of years ago. Vista revealed active stellar nurseries in the galaxy's outer halo, a sparse region that was thought to be essentially dead. These newborn stars are forming from gas that must have been somehow preserved in pristine condition for most of the galaxy's history, despite being surrounded by hot ionized material that should have prevented star formation. Even more mysterious were stars with chemical compositions that didn't match any known stellar formation process. Some contain unusual ratios of heavy elements that could only be produced by exotic stellar explosions or nucleosynthesis processes that don't occur in the modern universe. Others show evidence of having been contaminated by material from white dwarf stars or neutron stars, suggesting complex histories involving multiple stellar interactions. The strangest population of all was a group of stars near the galactic center that appear to be moving backwards through time. Their chemical compositions suggest they formed recently, but their orbital motions and spatial distribution match patterns that should only exist among much older stellar populations. These temporal paradox stars challenge fundamental assumptions about how stellar ages, chemistry, and dynamics are related. These unexpected populations are rewriting our understanding of galactic evolution. They suggest that galaxy formation was more chaotic and complex than astronomers had realized, with multiple episodes of star formation, chemical mixing, and structural reorganization happening simultaneously rather than in orderly sequence. But stellar populations aren't the only galactic structures that have surprised astronomers. Hidden throughout our cosmic neighborhood lies an invisible highway system that guides the flow of cosmic materials across vast distances. Invisible magnetic highways stretch across our galaxy, channeling cosmic gas and steering the birth of stars along routes that span thousands of light years. The Milky Way's magnetic field is too weak to affect everyday objects. You could hold the strongest galactic magnet in your hand and feel nothing. But across the vast scales of interstellar space, this seemingly feeble force becomes one of the most important shapers of galactic structure, guiding the flow of ionized gas, cosmic rays, and star-forming material along magnetic field lines that extend from the galactic center to its outermost edges. Think of iron filings scattered around a bar magnet, automatically organizing themselves into graceful curved patterns that reveal the invisible magnetic field. On galactic scales, cosmic gas behaves similarly, flowing along magnetic field lines and creating structures that mirror the galaxy's hidden magnetic architecture. These magnetic highways can funnel star-forming material across vast distances, triggering episodes of stellar birth in regions that might otherwise remain barren. VISTA's infrared observations revealed the magnetic field's influence in the structure of cosmic dust clouds. Tiny dust grains naturally align themselves with magnetic field lines like microscopic compass needles responding to the galactic magnetic environment. When infrared light passes through these aligned dust grains, it becomes polarized in patterns that trace the magnetic field's direction and strength. By mapping this polarization across the galaxy, astronomers created the first detailed charts of our galaxy's magnetic anatomy. The resulting maps revealed a magnetic field architecture far more complex and beautiful than anyone had imagined. The galactic magnetic field doesn't simply point in one direction like a giant bar magnet. Instead, it follows intricate spiral patterns that wrap around the galaxy multiple times, creating magnetic field lines that stretch for tens of thousands of light years. These magnetic spirals are intertwined with the galaxy's spiral arms, suggesting that magnetic fields and stellar density patterns evolved together in a cosmic dance that has been ongoing for billions of years. But the galaxy's magnetic field does more than just guide gas flows. It also acts as a cosmic particle accelerator, boosting cosmic rays to incredible energies as they spiral along magnetic field lines. These high-energy particles travel throughout the galaxy at nearly the speed of light, carrying energy and information between distant stellar regions and influencing star formation rates across vast distances. The magnetic field also plays a crucial role in stellar birth itself. When cosmic gas clouds collapse to form new stars, magnetic fields can either help or hinder the process depending on their orientation and strength. Strong magnetic fields can prevent gravitational collapse, keeping gas clouds from forming stars for millions of years. But under the right conditions, magnetic fields can also focus and channel collapsing material, accelerating stellar star formation and determining how many stars form in each stellar nursery. Recent observations suggest that the galaxy's magnetic field has been shaped by the same violent collisions that scattered stellar streams throughout our cosmic neighborhood. As smaller galaxies were torn apart by the Milky Way's gravity, their magnetic fields became tangled and twisted with our galaxy's field, creating the complex magnetic topology we observe today. But magnetic fields aren't the only hidden structures masquerading as familiar galactic features. What astronomers thought were distant star clouds turned out to be entire galaxies hiding in plain sight. For over a century, telescopes had cataloged numerous fuzzy patches of light scattered around our galactic neighborhood. These objects appeared to be loose collections of stars, possibly remnants of disrupted star clusters or distant regions of our own galaxy's halo. They were given unremarkable names and relegated to the astronomical equivalent of background scenery. Interesting, but not particularly significant. Gaia's precision distance measurements and VISTA's infrared revelations completely overturned this comfortable assumption. Many of these supposed star clouds were actually intact dwarf galaxies, complete stellar systems containing millions of stars, their own dark matter halos, and independent evolutionary histories spanning billions of years. They had been masquerading as Milky Way features because their low surface brightness and sparse stellar populations made them nearly invisible against the backdrop of our galaxy's more prominent structures. Think of looking at a crowded photograph and assuming that everyone in the background is part of one large group, only to discover later that several distinct families just happened to be standing in the same area. That's exactly what happened with these satellite galaxies. They appeared to be part of our galactic family when they were actually independent cosmic neighbors. The most dramatic example was the discovery that the Canis Major dwarf galaxy, long thought to be a disrupted star cluster, is actually the closest galaxy to our own. At only 25,000 light-years from Earth, this dwarf galaxy is being actively torn apart by the Milky Way's gravitational tides, creating stellar streams that wrap around our galaxy like cosmic ribbons. What astronomers had interpreted as random stellar debris was actually the death throes of an entire galactic civilization. Another surprise was the Sagittarius dwarf elliptical galaxy, which spent decades hiding behind the galactic center's dust and gas. This galaxy is so close that it's actually passing through the Milky Way's disk, yet it remained undiscovered until 1994 because cosmic dust made it nearly invisible to optical telescopes. VISTA's infrared vision finally revealed its true nature as a substantial galaxy containing over 1 billion stars. The satellite galaxy discoveries revealed that our galactic neighborhood is far more crowded than anyone had realized. Instead of being an isolated spiral galaxy surrounded by empty space, the Milky Way exists within a complex ecosystem of smaller galaxies, each following its own orbital path through our shared cosmic environment. Some of these satellites are ancient companions that have been orbiting our galaxy for billions of years. Others are more recent arrivals captured during the galaxy's ongoing expansion. These hidden galaxies also provide crucial information about dark matter and galaxy formation. Each satellite galaxy is embedded within its own dark matter halo, creating gravitational fingerprints that help astronomers understand how dark matter behaves on small scales. The satellites' orbital motions also trace the overall distribution of dark matter throughout our galactic neighborhood. But the discovery of hidden satellite galaxies raised an even more fundamental question about our cosmic address. Exactly where does our galaxy end and intergalactic space begin? Our galaxy doesn't have an edge. It just gradually fades into intergalactic space across distances that dwarf previous estimates of the Milky Way's size. For decades, astronomy textbooks confidently stated that our galaxy spans roughly 100,000 light-years from edge to edge, with most stars concentrated within a relatively compact disk. This measurement was based on optical observations that could trace the galaxy's spiral arms and stellar populations out to a certain distance before cosmic dust and the faintness of distant stars made further observation impossible. But VISTA's infrared surveys and Gaia's precision measurements revealed that defining the galaxy's edge is like trying to determine where Earth's atmosphere ends and space begins. There's no sharp boundary, just a gradual transition from dense stellar populations to sparse stellar halos to the near emptiness of intergalactic space. The process extends much farther than anyone had imagined. Think of trying to map the edges of a vast city by flying over it at night. The bright downtown core is easy to define, and you can trace the main neighborhoods and suburbs without much difficulty. But eventually, you reach areas where streetlights become sparser and houses more scattered. The city doesn't suddenly stop. It gradually transitions into farmland and wilderness across distances that might be much larger than the urban core itself. The new observations revealed that our galaxy's stellar halo extends at least 500,000 light-years from the galactic center, 5 times larger than the traditional disk diameter. This halo contains billions of stars scattered at such low densities that previous surveys missed them entirely. Many of these halo stars are ancient fossils from the galaxy's early formation, preserved in the outer reaches where galactic evolution proceeds more slowly. But even more remarkably, the galaxy's dark matter halo extends much farther still. Computer simulations based on Gaia's stellar motion data suggest that the Milky Way's gravitational influence reaches out to nearly 2 million light-years, encompassing a volume of space large enough to contain thousands of galaxies the size of our traditional stellar disk. Within this enormous gravitational sphere of influence, the distinction between the Milky Way and its satellite galaxies becomes blurred. The large and small Magellanic Clouds, traditionally considered separate galaxies, may actually be embedded within our galaxy's extended dark matter halo. Other satellite galaxies that appear to be independent systems might actually be gravitationally bound components of a single vast galactic structure. The expanded definition of our galaxy's size has profound implications for understanding galactic evolution and the cosmic environment of our solar system. Earth doesn't just orbit a star within a galaxy. We're embedded within a vast gravitational ecosystem that extends across millions of light years and contains dozens of satellite galaxies, countless stellar streams, and enormous reservoirs of dark matter and cosmic gas. This cosmic context becomes even more important when considering our galaxy's relationship with its neighbors, because the new observations revealed that the Milky Way isn't an isolated island universe, but part of an intricate network of gravitational connections that span our entire cosmic neighborhood. The combined revelations from Vista and Gaia have fundamentally rewritten the story of how our galaxy formed and evolved over the past 13 billion years. Traditional models of galactic evolution described a relatively peaceful process where our galaxy slowly accumulated mass over cosmic time, gradually building its spiral structure through orderly star formation and gentle gravitational interactions. This picture portrayed the Milky Way as a stable, mature system that had reached equilibrium billions of years ago and now quietly rotates through space without major upheavals. The new observations revealed that this textbook narrative was completely wrong. Our galaxy's history is a violent saga of cosmic cannibalism, catastrophic collisions, and ongoing structural evolution that continues today. Rather than forming through gradual accretion, the Milky Way grew primarily by devouring smaller galaxies, incorporating their stars, gas, and dark matter into an ever-changing galactic architecture. Think of the difference between watching a nature documentary about a peaceful meadow versus discovering that the same location was actually the site of multiple volcanic eruptions, floods, and forest fires over geological time. The serene present-day appearance masked a violent and dynamic history that shaped every aspect of the current landscape. Galactic archaeology, the technique of using stellar ages and chemical compositions to reconstruct cosmic history, revealed that our galaxy experienced at least 3 major collision events that fundamentally reshaped its structure. The destruction of Gaia Enceladus 8 billion years ago nearly tore the galaxy apart, scattering stars throughout the galactic halo and triggering massive episodes of star formation. Subsequent collisions with smaller galaxies continued to add stellar populations with distinctive chemical signatures that remain detectable today. But the violence wasn't limited to ancient history. Stellar streams from recently disrupted galaxies show that galactic cannibalism continues in the present day. The Sagittarius Dwarf Galaxy is being actively shredded by the Milky Way's gravity, with its stellar remains creating visible streams that wrap around our galaxy multiple times. This ongoing destruction will continue for billions of years as our galaxy consumes its remaining satellite systems. The archaeological evidence also revealed that star formation hasn't proceeded steadily over cosmic time. Instead, the galaxy experienced dramatic bursts of stellar birth triggered by collision events, followed by quieter periods when star formation rates declined. These episodes of cosmic baby booms and busts are preserved in the age distributions of stellar populations throughout the galaxy. Perhaps most remarkably, galactic archaeology showed that our galaxy's spiral structure is much younger than the galaxy itself. The current spiral pattern formed within the past few billion years through gravitational interactions with satellite galaxies and internal density waves. Previous spiral structures existed earlier in the galaxy's history, but were destroyed and reformed multiple times as the galaxy evolved. The rewritten galactic history has profound implications for understanding planetary formation and the development of life. The violent early epochs would have created hazardous environments where planetary systems could be disrupted by stellar encounters and radiation from stellar explosions. The galaxy's gradual transition to a more stable configuration may have been necessary for complex life to evolve, But our galaxy's dynamic history extends beyond its own boundaries, connecting it to a vast cosmic web of galactic relationships that spans millions of light years. Our galaxy isn't isolated in space. It's part of a gravitationally bound family of over 80 galaxies connected by invisible bridges of dark matter and cosmic gas. The local group, as astronomers call our galactic neighborhood, spans roughly 10 million light years and contains three major spiral galaxies: the Milky Way, the Andromeda Galaxy, and the smaller Triangulum Galaxy. For decades, these seemed like independent systems that happened to exist in the same cosmic region. But the new three-dimensional maps revealed that they're actually components of a single complex gravitational ecosystem with hidden connections that span the entire group. Think of what appears to be several separate islands in an archipelago, only to discover during low tide that they're actually peaks of a single underwater mountain connected by hidden ridges. That's exactly what Vista and Gaia revealed about our galactic neighborhood. What appeared to be isolated galaxies are actually connected by vast networks of dark matter filaments and streams of cosmic gas. The most dramatic discovery was a bridge of hydrogen gas stretching between our galaxy and Andromeda, spanning over 2 million light years of apparently empty space. This gaseous bridge contains enough material to form billions of stars, yet it had remained completely invisible to previous observations because it's too diffuse to emit detectable light. Only by using sensitive radio telescopes to map hydrogen emissions could astronomers trace this cosmic umbilical cord connecting the two largest galaxies in our neighborhood. But the connections extend far beyond simple gas bridges. Computer simulations based on the new observational data revealed that all the galaxies in the local group are embedded within a single enormous dark matter structure called a dark matter halo. This invisible scaffolding guides the motion of every galaxy in the group, determining their orbital paths and influencing their evolution over cosmic time. The gravitational interactions within this dark matter framework are driving the galaxies toward an eventual cosmic collision. In roughly 4.5 billion years, the Milky Way and Andromeda will merge into a single massive galaxy that astronomers have nicknamed Milkomeda. This collision will completely reshape both galaxies, scattering stars across vast distances and triggering massive bursts of star formation as gas clouds collide and compress. But the local group isn't an isolated system either. It's part of an even larger structure called the local supercluster, which contains thousands of galaxies spread across hundreds of millions of light years. The new observations revealed that our entire galactic neighborhood is slowly flowing toward a massive concentration of galaxies called the Great Attractor, pulled by gravitational forces that operate on the largest scales in the universe. These cosmic connections mean that our galaxy's fate isn't determined solely by internal processes like star formation and black hole activity. External gravitational influences from neighboring galaxies, dark matter structures, and large-scale cosmic flows all play crucial roles in shaping our galactic evolution over billions of years. The discovery of these hidden connections transformed our understanding of where we live in the cosmic hierarchy, revealing that Earth exists within nested layers of gravitational influence that extend from our solar system to the largest structures in the observable universe. Every revelation about our galaxy's hidden complexity has rewritten our cosmic address, placing Earth within a far more dynamic and interconnected universe than we ever imagined. Just 50 years ago, our cosmic address seemed straightforward. Earth orbits the Sun, which is one star among billions in the Milky Way galaxy, which exists as an isolated spiral galaxy in a largely empty universe. This address implied that we live in a stable, predictable cosmic environment where galactic evolution proceeds slowly and major changes happen on timescales much longer than human civilization. Today, that simple address has exploded into something far more complex and dynamic. Earth orbits a migrant star that has traveled thousands of light years from its birthplace, carrying our solar system through changing galactic neighborhoods over billions of years. Our sun exists within a galaxy that is constantly consuming smaller neighbors, embedded within vast streams of stars torn from destroyed galaxies, and permeated by invisible magnetic highways that channel cosmic materials across enormous distances. Think of updating your home address from simply listing your house number and street to including detailed information about geological fault lines, underground water systems, soil composition, local weather patterns, and the migration routes of every animal species in your ecosystem. That's the level of cosmic environmental complexity that modern astronomy has revealed about our galactic neighborhood. We now know that our galaxy doesn't exist in isolation, but as part of a gravitationally bound family of over 80 galaxies, all embedded within a dark matter structure that guides their evolution over cosmic time. This galactic family is itself part of larger cosmic structures that extend across hundreds of millions of light years, creating a hierarchical address that connects our local environment to the largest structures in the observable universe. The dynamic nature of this cosmic address means that Earth's galactic environment has changed dramatically over geological time and will continue evolving in the future. 4 billion years ago, our solar system existed in a different galactic neighborhood with different stellar neighbors, different radiation environments, and different cosmic hazards. 4 billion years from now, we'll be in yet another location as our galaxy collides with Andromeda and reshapes the entire local group. This dynamic cosmic context has profound implications for understanding the development of life on Earth. The gradual migration of our solar system from the galaxy's more dangerous inner regions to its safer outer suburbs may have been crucial for allowing complex life to evolve. The timing of major galactic collisions and the resulting episodes of increased cosmic radiation may have influenced mass extinction events and evolutionary bursts throughout Earth's history. But our expanded cosmic address also reveals unprecedented opportunities for the future. We're not trapped within a static galactic environment, but part of an evolving cosmic ecosystem that will create new stellar neighborhoods, new planetary systems, and new possibilities for life and intelligence to emerge. The ongoing collision between our galaxy and its neighbors guarantees that the cosmic environment will continue changing and creating new opportunities across astronomical timescales. Understanding our true cosmic address transforms astronomy from a study of distant objects to an exploration of our own extended cosmic environment and evolutionary history. The discoveries revolutionizing our understanding of the Milky Way are transforming how astronomers study every galaxy in the observable universe. For over a century, astronomers have used distant galaxies as laboratories for understanding cosmic evolution, assuming that what they saw in far-off galactic systems represented the same processes happening in our own cosmic neighborhood. But this approach was fundamentally flawed because we couldn't see the detailed structure and complex history of distant galaxies with anywhere near the precision available for studying our own galactic home. The revelations about the Milky Way's hidden complexity, violent collision history, and ongoing evolution have forced astronomers to completely reconsider their interpretations of distant galactic observations. What appear to be simple, well-understood galactic systems may actually be as complex and dynamic as our own galaxy, with hidden stellar populations, ongoing merger events, and intricate structural details that remain invisible at cosmological distances. Think of trying to understand human society by observing cities from an airplane flying at 30,000 feet. You might see the overall layout of buildings and roads, but you'd miss the complex social interactions, hidden communities, and dynamic changes happening at street level. That's been the situation with extragalactic astronomy. We've been studying galactic societies from cosmic distances without understanding the detailed processes that actually drive galactic evolution. The Vista and Gaia discoveries have revealed that stellar migration, chemical mixing, and structural evolution happen on much more dynamic timescales than anyone realized. This means that galaxies we observe at different cosmic distances, and therefore different epochs in cosmic history, may represent snapshots of rapidly changing systems rather than stable configurations that persist for billions of years. The evidence for widespread galactic cannibalism in the Milky Way suggests that most galaxies grow primarily through mergers rather than smooth accretion of cosmic gas. This has revolutionized models of how galaxies form and evolve throughout cosmic history, explaining observed properties of distant galaxies that had puzzled astronomers for decades. The discovery of extensive dark matter substructure around our galaxy provides templates for understanding similar structures around distant galaxies. Astronomers can now use the Milky Way as a detailed test case for theories about how dark matter behaves on galactic scales, improving predictions about galaxy formation throughout the universe. Perhaps most importantly, the three-dimensional mapping techniques pioneered with VISTA and Gaia are being applied to increasingly distant galactic systems. Next-generation telescopes will extend these methods to nearby galaxy clusters, revealing the detailed internal structure and evolution of hundreds of galaxies simultaneously. The magnetic field discoveries are driving new investigations of cosmic magnetism throughout the universe. Astronomers now realize that magnetic fields may play crucial roles in galactic evolution that had been completely overlooked in previous theoretical models. Even the techniques of galactic archaeology are being extended to distant systems, using stellar populations in nearby galaxies to reconstruct their formation histories and collision events. This cosmic forensics is revealing that violent, dynamic evolution may be the norm rather than the exception for galaxy formation throughout cosmic history. The Milky Way has become the cosmic Rosetta Stone, providing the detailed understanding needed to interpret observations of galaxies throughout the observable universe. We've only just begun to explore the hidden universe that surrounds us. The revolutionary discoveries from VISTA and Gaia represent the first chapter in a new era of galactic exploration that will extend far beyond anything we've accomplished so far. Next-generation telescopes and space missions currently under development will push the boundaries of cosmic cartography to unprecedented scales and precision, revealing aspects of our galactic neighborhood that remain completely invisible today. The European Space Agency's upcoming Euclid mission will map the three-dimensional distribution of dark matter throughout the local group and beyond, creating the first detailed charts of the invisible scaffolding that shapes galactic evolution. These observations will reveal how dark matter streams connect different galaxies and trace the cosmic web filaments that channel gas and galaxies across millions of light years. Think of having detailed street maps of your city, but no knowledge of the underground infrastructure, the water pipes, electrical cables, subway tunnels, and sewage systems that actually make urban life possible. That's where we are with galactic astronomy today. We're just beginning to map the invisible infrastructure that makes galactic civilization possible. The Nancy Grace Roman Space Telescope, set to launch later this decade, will conduct infrared surveys that dwarf even VISTA's comprehensive mapping efforts. This space-based observatory will reveal stellar populations throughout the galactic halo with unprecedented detail, potentially discovering entirely new categories of stellar fossils that preserve information about cosmic epochs we haven't yet explored. But perhaps the most exciting frontier involves time domain astronomy, studying how galactic structures change over months, years, and decades rather than assuming they remain static. Advanced monitoring systems will track stellar motions, magnetic field evolution, and dark matter substructure as they evolve in real time, revealing the dynamic processes that drive ongoing galactic evolution. The combination of artificial intelligence and massive astronomical data sets promises to uncover patterns and connections that human astronomers would never notice. Machine learning algorithms trained on VISTA and Gaia data are already discovering new stellar streams, identifying unusual stellar populations, and predicting where undiscovered satellite galaxies might be hiding. These computational techniques will become increasingly powerful as datasets grow larger and more comprehensive. Future gravitational wave detectors will add another dimension to galactic exploration by detecting the mergers of black holes and neutron stars throughout our cosmic neighborhood. These cosmic collisions will provide information about the galaxy's most extreme environments and reveal populations of compact objects that remain invisible to traditional telescopes. Perhaps most remarkably, the techniques developed for mapping our own galaxy are being scaled up to study the local universe. Within the next decade, astronomers will have three-dimensional maps of stellar populations throughout the local group, revealing the detailed structure and evolution of dozens of galaxies with Milky Way levels of precision. The greatest discoveries may come from completely unexpected directions. Every major breakthrough in galactic astronomy has revealed phenomena that no one had predicted or imagined. The hidden universe surrounding us undoubtedly contains structures, processes, and connections that will surprise and astonish us just as much as the discoveries we've already made. We stand at the beginning of an age of cosmic exploration that will transform our understanding of where we live in the universe and how we came to be.